Afternoon, everyone. So our topic is about integrate the traffic signal control from Synchro to SUMO. The outline of my presentation today will be basically contain 3 parts. First, I will start with a brief introduction and our motivation, and then we will do an introduction about our proposed semi-automatic 4-stage traffic signal control integration, and then we will also introduce our case study afterwards. And then we will do a conclusion and explain our future step. And to begin with, just to do a recap, since we are using Synchro and SUMO, we both know that SUMO is a microscopic simulation. For Synchro, it's a macroscopic one, which they focused more on traffic at a low level of detail, and the traffic stream is often represented in an aggregated level. And here goes to when and why we are considering using the simulation integration. So basically, we think there might be 3 scenarios that the integration is needed. One is focusing on the large-scale simulation. So basically, when we're considering a simulation network in urban or regional level, if we have some simulation platform in hand, extracting the network features from one to another would be more efficient. And then another scenario goes to multi-scale simulation connectivity. So seamless connectivity and the communication across different simulation platforms could be crucial, and integration might play a very critical role here. And for the third scenario would be data sharing. So sometimes when we're asking the data, some of the data agency could only provide data from other simulation platform, and that's why the data integration and the integration from different simulation platform is needed. And therefore, the aim of our study, by studying the traffic signal control integration from Synchro to SUMO, is to understand the feasibility and the effectiveness of simulation integration, specifically the traffic signal part in our major study, and also to identify the potential obstacles and the problem as well. And for further information, our study area focuses on the downtown Seattle in the United States. And here, I will do a brief introduction for the Synchro for those of you who are not familiar with it. So it's typically being widely used in specifically the public agency in the United States, and they are basically using them for traffic signal optimization. So when we asking data from the traffic agency, we probably could acquire the data from the Synchro part. So that's why it triggers our problem to integrating the traffic signal from Synchro to SUMO. And since SUMO is our friend for all of us, so I won't do any further introduction for SUMO. And we also conducted some of the review for the current packages that doing the platform conversion. So we know that SUMO has network convert. It can convert network from vSIM, but unfortunately there's no Synchro available. And however, also some of the users also mentioned that there's manual work is suggested after we do the conversion. And there's also another platform vSIM. They are saying that they are available to import Synchro from vSIM, but often the Synchro will be the latest version, and also there's also some report mentioned that there are multiple errors may occur if actual controller timing sheets are not matched. So with that, we propose our semi-automatic method. So we basically have 4 stages, with first stage for the data preparation, and the second stage connection to direction mapping. Third stage is the signal phase mapping, and the 4 is for data revision and output. Minjian will introduce this in detail.
Okay, let's go to some more technical part. This is the overall flow chart. Don't be afraid, I will go through most of the steps. So we divide it into 2 stages because it's a complex process, and also there are some network discrepancies between the SUMO format and the Synchro format. In the stage 1 data preparation, we generate the SUMO network from the OpenStreetMap. But the Synchro network, we got it directly from City of Seattle, which is a bit old. So first of all, we review all the format. The Synchro was in a CSV format with different definitions of nodes, links, lengths, time plans. While SUMO is more like a XML format with the HTML logic junctions. So most of them are actually comparable, right? Because nodes and junctions, they are actually identical. But one of the challenges is for signal control. Because in Synchro, it's more likely use the traditional time plans and phases, like the spreadsheet. But in SUMO, we are using the TLL logic with the state-based signal plan. So during the preparation stage, we have to pick up our conversion area and also creating an ID mapping table between Synchro and SUMO. So each signalized intersections are matched with each other in two different formats. Here is a sample of the Synchro example and SUMO example. You can see, is it the same thing? Yeah, it's very different. In the Synchro, it used the northbound, westbound to represent each movement. And in the phases, it's used a phase number with the ring barrier control number in order to link them together. In the SUMO, you can see on the part we are using the connections and connection index. And in the phase state, it used the bigger G and small r to represent the green and red. This is one of the intersection example. I draw this chart in order to show what the link index are and what the inbound edges and for different movements. So in the stage 2, we are trying to map each movement, or we call it connections in the SUMO, to be able to find the corresponding label in the Synchro, like which one is northbound left, which one is southbound right. So yeah, one thing we noticed in SUMO, the inbound links are numbered in the clockwise pattern starting from the 0 to 12 clock, and the pedestrian phases is specified afterwards. So yeah, here is our proposed framework. One of the challenges we are seeing is the roads at intersection are not perpendicular to each other, and they may be also not aligned with the north-south or east-west. I just draw a small chart, but please bear with my drawings. For example, this is one example we see in our data. In the Synchro, we have eastbound, westbound, southwest, and northbound. And the road geometry is like this. So our first step is to retrieve the information from both networks. From Synchro, it's for these 4 different movement labels. And for the SUMO, we get all the inbound unique edges for an intersection. Then we calculate the delta x, delta y, and slope based on the 2 nearest points to the intersection center. Why we want to calculate that? Because we want to find all the possible candidates for each inbound direction. For example, for the southwest bound, we will look the 90 degree. It's 45 degrees before and 45 degrees after in order to find all the possible inbound edges. And next step, we will do this in 2 iterations. In first iteration, we will look each inbound direction from Synchro to see if there is one or multiple inbound edges that fall into this criteria. For example, for southwest, you can see there are 2 inbound edges, which we don't know which one to choose, right? Because one could be southbound and another one could be westbound. So we just move forward. But when you look at the westbound, you'll see there is only 1 inbound edges fall into this criteria. So we will assign the westbound to actually this. Do we have a pointer? Oh, sorry. We will assign the westbound to this one. We will call this as westbound. So in this case, we have removed one of the. Oh, okay, thank you. Yeah, we have removed one of the candidates from the list. Then we just go to the next inbound direction and find all the possible solutions. After 2 or 3 iterations, for most intersection, we are able to perfectly match the inbound labels with all the inbound edges. Once we have the inbound edges and the label mapping, we will be able to assign the traffic bound, which is westbound left, through, or right to each connections. So for the stage 3, we want to do the signal phase mapping. Most of our intersections is use the actuated signal control, and it may have different rings and barriers. This is a typical ring barrier control with 8 phases. And there are and this is one of the examples from the Synchro. You can see this is a 3 ring with pedestrian phases. And this is a barrier 1, and this is the second one. And for the SUMO, we want to convert it to the line-based state. It's like a green, red, or yellow. There are actually multiple ways to do it. One thing we noticed is really great is the NEMA type controller, which is contributed by Maxwell and also other signal contributors from SUMO, which is very nice. But one of the limitations is it only supports up to 2 rings. So, but we have 3 rings. Unfortunately, we have to implement some of logic using the next feature in the SUMO TL logic. The next feature is like you can specify multiple phases in the future, and the SUMO will be able to pick one of them based on the actuated detector from the simulation. We have divided the stage 3 into 3 steps. First one, we use the breadth first search, trying to find all the valid phase combinations from the Synchro data directly. So you can see the 145 will be able to the next phase might be 157 or 345. Then when we have all these charts, we will be able to use the previous result and convert it to a line-based state, like a GRR, GGRR, for all the green phases. With that, we can compare the transition between 2 green phases and fill in the yellow and red phases if needed. So the all red phases is needed for each barrier, while the yellow phases is needed between each green phase pairs. Finally, we will do a data revision to make sure there was no conflict phases. All the phases from Synchro and SUMO have the same number, and also do some manual revisions if needed based on the result. So here is one of the results. The upper part was the signal timing phasing from Synchro, and the down part was the phase from the what we generated from our small Python script.
And next we will do a case study. So basically, this figure, the figure on the left shows our study region, and the network feature in our SUMO network contains like a pedestrian line, bus step, link lateral, and we also use TAZ for the origin and destination trip assignment. And to give you a general idea, so basically that's how the study area looks like and how it looks like in SUMO. And the left part shows like what's the traffic signal we're gonna using from the Synchro network. And here is just a case to show like how complicated those intersections could be. As Minjian also mentioned, that's why we are considering doing traffic signal conversion ourselves. So basically, we will encounter several complicated intersections, and we also, even for cross intersection, we can encounter multiple cases with like some of the direction not protected or being protected. And this is also the results that Minjin just showed. One thing I would like to highlight here is that we also add a column, which is a name here in SUMO to mention the face name. That is a face name actually from the Synchro part. So that's why. So for further validation, we can use this to do the check. And here is the results. So basically, our method works well in a simple case, specifically when we focus only on one major street with 5 intersections, we can get like 100%. But things could be more complicated when we go to a network level. So in summary, we get 85%, although not bad, but we still have something to go. And here is to show a display of how our simulation looks like. So basically, everything works well. And one thing I would like to mention is that this simulation network and also our integration method is all public right now. And you can find the GitHub link in our paper. And you can see that we cover like bus, pedestrian, and the link lateral, and also the traffic signal looks good. And for the conclusion, the major takeaway is we propose an automatic 4-stage approach, and those approach has been done in Python, and our tested network shows not bad results. And for future step, we can do several things. One, we can test our algorithm in a more larger network, or we can do the algorithm enhancement because we still have like 50% to go. And also, we can do some advanced features for example, like a coordinated signal control conversion. And also, we could think about doing the entire integration from Synchro to SUMO, not just the traffic signal, but also the other network features. So that's basically our presentation. Thanks for your attention, and do you have any questions?